Thank you, Mike. And it's good to see everyone early in the morning. So I'll continue my discussion of duality in the topological holography framework. So yesterday, I mainly introduced what is a sandwich. I gave this very explicit example of how to realize the 1+1D transverse fluid icing as a sandwich, which means to write it in a way more complicated way with a toric code in the book and then a gap boundary on the top, but then some dynamical terms on the lower boundary. So just to remind you, I've drawn the picture here where I illustrated all the operators, including the bulk stabilizer, the top boundary stabilizer, and also the bulk logical operators that define the symmetry sectors, the symmetry charge and flux sectors, as well as the various dynamical terms that live on the bottom boundary, and I've also indicated their correspondence to the terms in the transverse field icing model. So that later today, I'm going to do a slightly different version with a slightly different top boundary, and we're going to see how the correspondence is turned on its head and how we can induce Kramer-Vanier transformation, Kramer-Vanier duality just by changing the top boundary. Okay, so we'll get there. But before that, because I ended a little bit early yesterday before I can finish my example of some other interesting sandwiches. So let me finish the discussion of that. And the only one that I didn't get to talk about is this 3+1D example. So this will eventually be a 2+1D sandwich, but in the book, it's the 3+1D toric code. So it's just a generalization of the 2+1D version. And as a topological order, it's what people call the Z2 topological order or Z2 gauge theory. It's a lot of different names and maybe confusing names for it. But basically, the fractional excitations within the book would be a point charge excitation and a Z2 flux loop excitation. Okay, so very simple kind of topological order. And then very similarly, we can choose some gap boundary conditions on the top. So I won't get into the details of all possible kinds of boundary conditions. I just would like to say at least there's some simple ones you might imagine where, for example, the bulk charge can condense. That is actually what people might call the rough boundary. And the other one is where the flux loop can condense, and that is usually called the smooth boundary, according to some lattice realization, but it's not important. So these two ways, so it's either charge condensed or flux loop condensed. These will actually give rise to sandwich with different symmetries, because as we discussed yesterday, the choice of the bulk together with the top boundary determines what kind of symmetry the sandwich will have. So in particular, we know that the sandwich will come out of the set of logical operators that runs parallel to the boundary. Right? So here the boundary is what we have chosen as XY plane. So we can take all the logical operators that run parallel to it, and there are several of them. One is a big membrane operator. This green membrane operator I've drawn, this is the membrane operator for the loop excitation. And if we have a complete membrane operator, that is one of the logical operators, as well as the red string operator running around the big cycles, the non-trivial cycles. So the string operator, of course, will correspond to the charge excitation if they ever end in the bulk. So depending on which boundary we have, these operators will take turns to become the symmetry or the flux sector indicator. For example, if we have the charge being condensed on the top, meaning that charge hopping doesn't give rise to anything non-trivial, And if that's the case, then we'll see that these line operators, which basically hop the charge around, they will be automatically fixed to be 1, unless there's a defect, right? But given the top boundary, these operators will be fixed to be +1. And then in that case, the membrane operator will become the symmetry operator, and that's the usual so-called zero form Z2 symmetry that we talk about for a 2 + 1D system. So if the charge is condensed on the top, we get a 2 + 1D sandwich with a zero form global unitary Z2 symmetry, and it's non-anomalous. So it's quite analogous to this other case we talk about. So this is, let me write it here, zero form Z2 symmetry. On the other hand, if we have flux loop being condensed, then this green membrane will be set to a particular value. So if there's no defect on the top boundary when the flux loop condenses, then the whole green membrane will take eigenvalue 1. And in that case, it's the red lines that become the symmetry of the 2 + 1D sandwich, and that becomes the Z2 one-form symmetry of the sandwich. So we'll get a 2 + 1D system with one-form Z2 symmetry. Okay. Yes.
So the gap boundary of the 3 + 1D Toric is not just characterized by.
Yeah. 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 That's a subtlety I didn't want to go into, but you know too much. So yes, so there's another so-called twisted smooth boundary, which can be obtained by, in a sense, attaching Z2SPT to the boundary. And in that case, it still gives a sandwich with Z2 one-form symmetry.
But even in addition to that, we can do many other things, right? We can put the 2 + 1D topological order.
Yeah, we can also put other 2 + 1D topological order on the top boundary. But I think we need to draw a line somewhere. So if we allow anything, then there will be infinitely many different top boundaries. But for the sandwich construction, maybe not all of these top boundaries are useful. Because when we consider how the top boundary affects the bulk, we'll try to tunnel whatever is on the top to the bulk, try to create a charge or create a twist. So I think maybe it's related to this concept of local. Is that what Xiaogang called local? Meaning that any excitation on the top boundary can go into the bulk. So if there are fractional excitation only confined on the top boundary, then it doesn't really affect the sandwich structure because it doesn't talk to the bulk. It doesn't talk to the bottom boundary. I'm not sure if the word local is the correct one, but there's some notion that describing that that we don't need to add arbitrary 2D topological order on top. Yeah, Xiaogang.
Gap boundary means if you attach another topological order to gap boundary, we still call that equivalence. So we can quotient out this kind of equivalence, then define some kind of so-called minimal version. I don't know whether useful or not, but
yeah, I think that would be useful. I'm not exactly sure if up to that equivalence we are left with just the 3, the rough, the smooth, the twisted smooth. So far, people have been mostly talking about those 3.
But the condensing boundary, the twisted and condensing boundary, are they kind of equivalent as far as the sandwich construction is concerned?
Yeah, great question. So, right, this is something I'm still trying to understand. So for this example, it's actually more tricky to see. But for the fermionic one, we have a better understanding. So if the bulk is a fermionic toric code, you can start from a smooth boundary, and then you can add a P plus IP superconductor, an invertible fermionic phase to change the boundary type. So in that case, we see that these two, which differ by P plus IP, actually gives you a different sandwich, meaning that the the symmetry sectors are labeled differently. So in that case, of course, because one is kind of non-abelian, the P plus IP one, it kind of gives you a non-abelian sigma anion once you gauge it, while the trivial one doesn't give you a non-abelian one. So the difference is more obvious. Well, in this case, the difference is abelian, and moreover, they give rise to the same ground state degeneracy on 2 torus. So on 2 torus, we don't really, so if we just have a 2 torus sandwich, we don't really see the difference. But my suspicion is that if we go to more complicated manifold, where double semyon and toric code would have different ground state degeneracy, which it can be, there are papers about that. There's some non-orientable manifold where you can put double semyon and toric code on it, and then they have different ground state degeneracy. In those situations, I think we might see a difference. So I hesitate to say, because I don't fully understand yet, but I think that might be the case. Yes.
If you want to talk about the bottom boundary, because the twisted M tends to be the Levin-Gu boundary.
Sorry, what's the question?
Oh,
You're asking the bottom boundary, whether the twisted...
yeah, for the bottom boundary, wouldn't the twisted M be different than the M? Because it'd be 2 different SPTs.
Yeah. So if we terminate the top boundary in the same way, and then the bottom boundary, one is twisted, the other is not twisted, they will correspond to different phases. I think the question I was answering for Shuheng is, as a top boundary, how they give rise to different sandwich with different symmetries.
More questions about the bottom boundary. It's very similar in spirit, right? I think it's very easy to see that whatever you do in the bulk will give me a symmetry at the bottom boundary. But it's not obvious to me that these are all the symmetries of the bottom boundary, right? If I put some non-trivial dynamics on the bottom boundary, I could have more symmetries that are like some lines that are completely confined to the bottom boundary. So there must be some constraint you're imposing that sort of the only symmetries you get at the bottom are the ones you get from your sandwich, and there's nothing, right? If I make a very non-trivial bottom boundary, I clearly can put the dynamics on the bottom boundary that should sort of localize there and has more potential lines in membrane. So is there some, in this sandwich construction, is there some constraint that sort of tells me that the bottom boundary doesn't have any independent symmetries?
The bottom boundary, the bottom boundary can definitely have more symmetry than is dictated by the bulk and the top boundary. So that's just saying that the sandwich structure doesn't know about this extra symmetry. It doesn't control the symmetry sectors in the way that we do it.
Which is what this is like going to, is that it's supposed to encode all the symmetry structure of the.
Okay.
So you're not making that claim. You're saying there's like you can geometrize some of the symmetries.
I see. Yeah. I guess that might be the difference between symmetry TIP and my more lattice oriented thinking that
Sense, I'd very much like to understand how SymTFT is related to what you're doing, but so maybe I just need to make the lattice more complicated until I get all the lattice.
Yeah, the lattice I allow any generic terms. So if I allow any term on the bottom boundary, then I'll generically break any symmetry that's not dictated by the bulk. But of course, I can tune to a point where it has a more symmetry. Yeah. Okay, great. Yes.
So it seems like when you have you only have one membrane, but obviously you have 2 directions for the line operators. So do those give you like 2 different symmetries or?
Yeah, great question. So for one form symmetry, and this is one form symmetry, what I'm drawing on a 2 torus. So one form symmetry, it has symmetry operators of all different kinds of shapes. It can be trivial cycle or non-trivial cycle, and the non-trivial cycle can go in different directions. It's the same symmetry, it's just the symmetry operator have different forms. Yeah. Okay, great. So that's all I want to say about the 3+1D case, and I'll come back to the 2+1D sandwich realizing the 1+1D Ising model. Okay, and my goal today is to explain how the Kramers-Manuel duality in the transverse field Ising model correspond to changing the top boundary from smooth to rough or rough to smooth, back and forth in this sandwich picture. That's my goal. Okay. All right. So let's first review how Kramers-Manuel happens in 1+1D transverse field Ising, and this is not the first time already in the summer school that this is being reviewed, so I'll be pretty quick. So the standard version goes like this, that you have the model, and notice that I've put a plus sign here. I already included the plus sign yesterday because this is a model with so-called periodic boundary condition, and in a minute we'll be talking about the one with anti-periodic boundary condition because we see that the charge sector and the flux sector actually map to each other under the Kramers-Manuel duality. Okay. So for this periodic boundary condition model, the Kramers-Manuel duality simply goes as follows, that we take the transverse field term and map it to the Ising coupling term, and we take the Ising coupling term and map it to the transverse field term. Okay, and we can explicitly check that once we map the terms like this, their operator algebra is explicitly preserved. For example, each operator squares to 1, and if they commute before, they still commute. If they anti-commute before, they still anti-commute. So the whole local operator algebra is preserved. Okay, so it looks fine until you consider some global quantity. For example, the Z2 symmetry operator, which is a product of sigma x. And we see that after the mapping, this becomes the product of all the Ising coupling term and becomes 1. Okay, so the symmetry operator basically is fixed to be 1. On the other hand, if we take the product of the Ising coupling term before the transformation, which we know should be 1, and we see that it actually maps to the Z2 symmetry. Right, so that means that both before and after the Kramers-Manuel duality, the Z2 symmetry should be just set to 1. And that's what basically what Shuheng was saying, that if we only look at the non-charged sector, the symmetric sector, and then this duality works fine. But if the symmetry operator can take value -1, then things will break down. Okay, so of course you can then check that once we do this mapping, the original, sorry, there's a coupling constant here. The original Hamiltonian with parameter G maps to the dual Hamiltonian with parameter 1/G. So this is what we always talk about, that the symmetric phase map to the symmetry breaking phase map back to the symmetric phase, but the critical point is invariant. It's a self-dual point. Very well. Okay. So the fact that if we restrict this whole duality mapping to the no charge sector, and this is the underlying reason why this Kramers-Manuel duality is a non-invertible symmetry, right? Because it doesn't square to identity, squares to this projector together with a translation. But we can, with some more tricks, we can make the mapping also work in these other sectors. So let's consider the sector let's try to make things work for the sector where it's charged. The symmetry is equal to -1. So every state is charged. Okay, and all we need is to modify this operator mapping slightly, and then we'll see what happens. Okay, So the operator mapping is almost the same everywhere except for the last term. So all the Ising coupling terms still map the same way. So Ising coupling term still maps to transverse field. And then all the transverse field except for one still map to the Ising term in the same way as before, but the last transverse field term, so this is for I not equal to n. But for the last one, we'll add a minus sign. For the last term, we'll add a minus sign. Okay? And you can see how this fixes the problem, because so this is Kramer-Vanier in the charge sector. Because now, if we take the symmetry operator and see what it maps to, you can check that this maps to -1. That's good, because originally it was -1, now it's still -1. And if we take the product of the Ising terms, and we see that this is 1, and this gets mapped to the new symmetry operator. Okay, so that means that before the mapping, I'm in the charge sector, but after the mapping, I'm in the no charge sector. So I start from a charge sector and maps to the no charge sector. Okay. But if we literally map the Hamiltonian terms like this, we'll see that the Hamiltonian terms actually changes. So this Hamiltonian term, if we literally change the Hamiltonian terms using that rule, we'll see that this maps to the H minus 1 over G, because the final transverse field term maps to minus sigma z, right? So the Ising coupling term at the boundary flips sign, and that is exactly what happens in H minus. So apart from this parameter change, we also map to the flux sector. Okay, so in the Kramer-Vanier duality, if we start from the charge sector with no flux, we map to the flux sector with no charge. Okay, so there's a permutation of symmetry sectors here. And I won't try to exhaust all possibilities, but I'll list the final result. So if we list the 4 sectors like this, so this eta can take value in plus minus 1, and the first one labels whether I have a charge or not, and the second one labels whether I have a flux or not. So this is plus minus 1, plus minus 1. Then under Kramer-Vanier, the 4 sectors map as plus 1, plus 1, going to plus 1, plus 1. That's over there. And then a minus 1, plus 1, 2, plus 1, minus 1, that's this part. And then plus 1, minus 1 goes to minus 1, plus 1. And finally, the sector with both charge and flux are kept invariant. Okay, so that means if I only look at one sector, of course this looks like a restricted mapping. But if I include all 4 sectors, then it will be just a permutation among the 4 sectors. Okay, and we can even do more. We can even explicitly compare the spectrum, the low energy spectrum in these sectors, and see that they match exactly. Okay, so this is because duality is supposed to be, well, I should say the word duality, different people mean different things, and I'm not trying to define it at all. And I'm probably using it in a way that's conflicting with some people's convention. But here, now I'm trying to use this topological holography, the sandwich picture, to try to talk about it. Then I'll try to be explicit about what changes and what does not change once I perform this duality transformation. And one thing that do not change, as we'll see here for this example, and we'll illustrate why that's the case using the sandwich picture, is that the low energy spectrum will actually exactly match with each other. Yes.
Invertible symmetry is actually invertible if we look at all the sectors at the same time.
In a sense, yes. But as I said, once we include 4 sectors, this is not a tensor product Hilbert space anymore. So in this one-dimensional chain case, we actually consider 2 copies of the Hamiltonian. One is H plus, one is H minus. And in the sandwich picture, we're considering this restricted Hilbert space. So if you only consider things in a restricted Hilbert space, then yes.
Eric, like, should I always think of non-invertible symmetries as being invertible under some suitable enlargement of the Hilbert?
Just for these kind of duality transformations. More generally, I don't know. No, in general, no, I think.
Can you emphasize on the low energy spectrum?
Because I can't compare the full spectrum. I don't think it works if the spectrum energy goes too high. I'm not. I don't.
Operator corresponding.
Okay, let's talk about it. Yeah, so I've only explicitly thought about the low energy part because the duality statement is usually about effective low energy theory, but yeah. Was there another question? Oh, Natty, yes.
It's not a question, it's a comment. Many people would like to put different sectors together and make a bigger theory, which includes many sectors. This is a very common view, but it's fundamentally wrong because there are some axioms of quantum field theory or also of the lattice systems that this construction violates. For example, correlation functions are not local. There's action at a distance. All sorts of things that are sacred in physics are not satisfied when you try to put the sectors together.
Okay, thank you.
This was outlined in a paper by Cassini et al., but according to Clay Cordova, I believe that those axioms don't apply to vector theories. I'm not completely familiar with the details, but this is what embedded a discussion. So, yeah.
I do not know what you're talking about, but I'm sure that if you ask Cordova, he will tell you what I just said. I'm 100% sure of this.
Okay.
I'm talking about Clay Cordova, right?
Yeah.
Okay.
Yeah. My plan today is to talk about all the sectors together and how they permute with each other. Okay. Yeah. So let me illustrate how the spectrum match, because usually when we talk about the symmetry breaking phase mapped to symmetric phase and symmetric phase mapped to symmetry breaking phase, obviously the low energy spectrum look different because the symmetry breaking phase has 2 ground states and the symmetric phase has only 1 ground state. But if you realize that if we restrict things to individual sectors, then they actually match, right? Because this is symmetric phase, this is symmetry breaking phase, and we have 4 sectors, and let's just look at ground state, for example. So for the ground state in the symmetric phase, there's 1 state that's +1 +1. In the symmetry breaking phase, there are 2 states. But one of them has charge 1, the other one has charge -1, right? So if you compare things here, it's 1 and 1. On the other hand, if we're in the symmetric sector and we insert a flux, nothing happens because, well, in the limit where it's just transverse field, then the system is not affected at all. And then we know that there's still just one ground state. So that actually corresponds to here, where there's one charged ground state in the symmetry breaking phase with no flux. Okay? And if we're in the symmetry breaking phase and we insert a flux, which means we flip the sign of one of the Ising coupling term, then there's frustration among the Hamiltonian term, and there are actually n ground states. Correspondingly, in the symmetric phase, if we look at the charge sector, if we force the wave function to have one charge, then we can pick where the charge is without changing the energy. So there are also n lowest energy states, and those two correspond to each other. Okay, and then you can do the exercise for the next for the last sector and for the excited states, the first, second excited states, and things all should match. Okay. So yeah, so and in later we'll use the sandwich picture, and I'll try to show you how that comes as a consequence of the fact that we can change the top boundary of the sandwich to induce the duality using a unitary circuit. Okay. And that's because it's unitary and permute all the sectors, then the spectrum should look the same. Okay, all right. Okay, so now I'm ready to go back to the sandwich picture and show how this is done by changing the top boundary condition. So maybe I'll just erase this board. Okay, and to talk about that, we need to discuss the other type of boundary condition for toric code, which is the rough boundary condition. And things look very similar, except that everything is swapped. Okay. So let me draw the toric code again. So this is 2 + 1 toric code. The bulk Hamiltonian terms are still the same, the 4-body sigma x and sigma z terms. But the top boundary is now rough. And this is what we mean by rough, that there's edges sticking out. Okay, and what that means in terms of Hamiltonian is that on the top boundary, now instead of having 4-body plaquette terms, we only have 3-body plaquette terms. So remember, for the smooth boundary, we had 3-body vertex term, but for the rough boundary, we have 3-body plaquette term. And the vertex term are still 4-body. Okay, so everything commutes, and this is gapped, and yeah. And the key difference from the smooth boundary is that now, if I drag a red line in the vertical direction, like this, a line of x, this will not create any excitation either in the bulk or on the top boundary. And we know that the red line is the string operator for creating the charge excitation. That means the top boundary has the charge condensed. So the rough boundary is charge condensed. And that makes all the difference. So previously, the smooth boundary is flux condensed, and now it's charge condensed. Okay. And very similarly, we can now talk about horizontal string operators and how that gives rise to the symmetry of the sandwich. And we have the same horizontal string operator. There's a WMX, and then WEX. The only difference is that now the top boundary fixes WEX, not WMX. So if the top boundary, every open plaquette is said to be 1, then this one is equal to 1, while the green one can have the freedom of being plus minus 1. So now the M string operator is the Z2 symmetry, while the E string operator labels the flux sectors. Okay, and this WYE, the red string operator running in the vertical direction, this one anti-commute with my new symmetry operator, so this is the Z2 charge. So you see that it's pretty much the same picture, except that I've swapped red with green and lattice with dual lattice. Otherwise, it's the same picture. Okay, good. So this is about the bulk, the top boundary, and then the string operator, the topological symmetry operator floating in the bulk. Yes. So with the choice of the top boundary, then if they further choose the bottom boundary, for example, to be in a gap state, then the whole sandwich will be in a gap phase. And then it becomes a question of which gap phase it is. There are 2 gap phases. One is symmetry breaking, one is symmetric. So yeah, in a minute, we'll see how the pair of top boundary and bottom boundary determines which phase we're in. Okay, so then we can talk about what happens on the bottom boundary, and what happens on the bottom boundary basically doesn't change, right? Because all we change is the top boundary, and the rule for the bottom boundary is that we can add terms, the commute with the bulk and commute with the top boundary. So the story is basically the same. Now we have these 3-body ZZZ terms. We have 3-body ZZZ terms, and we have a single body X term. It was exactly the same as before. However, now we need to make connection to the transverse field Ising model by relating the 3-body ZZZ term and the X term to the original spin 1/2 Ising coupling and transverse field terms. Yesterday, with the smooth boundary, we made the identification by realizing that the 3-body ZZZ term is equivalent to the product of 2 charge operators. 2 of the green lines multiplied together up to bulk terms, and the top boundary term is equivalent to the ZZZ term. Now it's the opposite. If we take, now that the charge operator is a red X string, right? So we take 2 of these red X string, and we multiply them together. And then we can further multiply the top boundary and the bulk term because they're said to be 1. So we multiply this term this term, this term, this term, and this term, and we see that this X operator becomes equivalent to the product of two charge operators. Okay, so the X term, the single X term, becomes the Ising coupling term. Right? Make sense? Yeah. So this becomes equivalent to the sigma z. And then using the operator algebra, the fact that the three-body ZZZ anti-commute with the nearest neighbor X to its left and right, we know that this ZZZ should be interpreted as the transverse field term. So it's exactly the same term, but their interpretation as the original transverse field degrees of freedom operators are different. Okay, good. Great. So now we see why changing from the smooth boundary to the rough boundary gives us the Kramers-Wagner duality, because these ZZZ and the boundary terms are the dynamical terms of the sandwich, right? And say they come with some coefficient. And when we change the top boundary, we're not doing anything to the bottom boundary terms. They're still the same terms with the same coefficient, and nothing happens there. However, their interpretation in terms of the Ising operators get flipped. And the transverse field term is now interpreted as Ising coupling term, and the Ising coupling term gets interpreted as the transverse field term. And that's exactly why when we do the duality transformation, G goes to 1 over G, right? So the terms got swapped. Okay. So the operator mapping is exactly what we would want. Okay. On the other hand, we can also see how the sectors are swapped, right? Not just how the dynamical terms are changed, but also how the symmetry and flux sectors are swapped. Because the symmetry and flux sectors, they're labeled by the eigenvalue of the horizontal string operators. So for example, the no charge, no flux sector is labeled by both the red and green string operator equal to 1, right? And then the other sectors are labeled by the other eigenvalues. And when we change the top boundary, we're not touching these horizontal string operators. They're floating in the bulk. They're below the boundary. They're below the top boundary. So we're not doing anything to those bulk string operators. So those bulk string operators, they still have the same eigenvalue. They're whatever they are. However, their interpretation is changed, right? It used to be that the red one is the symmetry operator. Now the red one labels the flux sector. And the green one used to label the flux sector, and now it labels the symmetry, the charge sector. And that's exactly why we see this, I guess I pushed it up. And that's exactly why we see the swapping of the sectors after the Kramers-Wagner transformation. Okay, so it's the take-home message is that nothing in the bulk and on the bottom boundary changes. It's just their interpretation in terms of the one-dimensional changes. And that's all you need in order to induce a duality transformation. Okay, no objection. Okay, good. Right, and the next thing I want to show is that this change in the top boundary condition from smooth to rough can be induced by what we call a sequential quantum circuit applied only to the top boundary. Okay, so I'm going to take the sandwich, and do some quantum circuit only on the top boundary. I'm not going to touch the bulk or the bottom part. I'm only going to touch the top part. And I'm going to do something unitary in such a way that I'm changing the boundary condition from smooth to rough. Okay. And because what I'm doing is unitary, that means the spectrum of the whole sandwich remains invariant. And that is consistent with what I'm saying here, that the low energy spectrum of the sectors should match exactly with each other. And actually, a further conclusion I can make is that because of a special property of the sequential quantum circuit, which preserves entanglement area law, that the wave function before and after the mapping also change up to, at most, entanglement area law. But that's a part I'm not going to say too much. Okay, so let me just draw the circuit I'm going to use and convince you that this kind of transformation can be done. Okay, so what I'm going to show is how to map from the rough boundary to the smooth boundary with a series of unitary gates applied along the boundary. So the sequential quantum circuit is actually going to, I'm going to apply it step by step, starting from a point, and then move to the right, and then eventually with the parallel boundary condition coming back to the left and complete the circle. Okay, so it's going to be many, many, many steps, actually linear steps in the length of the sandwich. But it's a stepwise circuit. So even though it has many steps, every step only acts locally on the one-dimensional top boundary. And that's what we mean by sequential for the circuit. Okay. So let me assume that I start from the rough boundary with Hamiltonian terms like that. And I'm going to do a bunch of control knot gates. So here's a control knot. Here's a control knot. So these yellow arrows are controlled knot gate, meaning that for the 2 qubit involved, if the first qubit is 0, it does nothing. While if the first qubit is 1, then it applies an X to the second qubit. This is control knot. Okay, so I choose a starting point anywhere along the top boundary, and then in the first step I will apply 2 control knot gates, and they commute. I can apply them together. And in the second step, I move to the second plaquette and apply a bunch of control knot gates, and then so on and so forth. And finally, I come back to this n-1 gate plaquette and do these gates. While for the last one, there's a little bit more complication. I need some gates that goes like this. Right. So you can roughly see why this circuit works, because, for example, there was a 3-body open plaquette term like that. In the first plaquette, it's XXX. And then after the first step of the circuit, it will shrink to a single X on the vertical edge. So this XXX become just a single X. So that vertical edge literally get decoupled from the rest of the system. And that's exactly what we want if we want a smooth boundary, because the smooth boundary want all the edges sticking out to decouple from the system. So that's and that works. And then going to the second plaquette, we see that the second plaquette also becomes a single X term on the second edge, and then it decouples, and step by step we'll decouple all the staking edges, and then the boundary becomes smooth. Okay. And there's one complication, because remember that these horizontal string operators we're not touching them. So their eigenvalues should remain invariant, and that should still be reflected before and after our circuit. For example, if we started in the sector where this green line is -1, which means it's the charge sector of the sandwich, now we should map to the flux sector of the new sandwich, right? Because charge sector and flux sector got swapped. And that means that eventually, once we convert it to a smooth boundary, we should have one defect because the eigenvalue of the green line is controlled by all the terms on the top. And if you follow this circuit, you will actually indeed see that there is this last term at this vertex, which basically inherit the eigenvalue of this green line. If it's -1, then this term will be -1. If it's +1, then it will be +1, so that everything will be consistent. Okay, so I won't try to show you all the details. This is just very standard algebra, but everything should work. Okay. Yes.
The circuit in 1D that
to Schumann circuit?
Not the projector part.
Yeah, I think it should. I think in these simple cases, we might even find how they're related. I haven't done the exercise, but I suppose, yeah, exactly. Yes.
So, can you say that in this 2+1 picture, the premise one year becomes the invertible symmetry. So,
premise one become a symmetry.
Invertible symmetry because you can kind of implement that by a circuit.
Sorry, can I try to make sure I understand the question? So you're asking whether we can consider Kremers-Vanier as a symmetry, as a non-invertible symmetry, or as an invertible symmetry?
Because it can be implemented like this unitary circuit.
Right. So you might say that, oh, this is fully unitary. You're not doing a projection anywhere, and it seems like it just takes sectors to sectors. But I need to say that this only works in the low energy sector where we have fixed the bulk and top boundary to be in their +1 eigenstate. So this is not a tensor product Hilbert space. If we start from a tensor product Hilbert space, we won't be able to get a fully invertible operator to implement that. Okay, great. Yeah, so hopefully this is, you're happy about the story about the Kremers-Vanier duality and how it's induced by a change of top boundary in the sandwich picture. And of course, the reason I'm doing this example so carefully is that I'll try to not show you, but just claim that this is a general result that applies to other sandwiches that you might want to construct. So starting from whatever sandwich, this 3+1D sandwich, we can start from one gap boundary and then apply a sequential quantum circuit on the top boundary to change the top boundary from one gap state to another gap state. And this will induce a duality in a similar sense. Okay, so this is using the word duality in a way that may not be the way you're using, but what we're literally doing is that we're inducing a transformation where the symmetric operator algebra remain literally the same because the symmetric operator algebra lives on the bottom boundary. so they're not changed at all. The symmetry charge and flux sectors might be swapped, but there's the same number of sectors, or at least in the simple abelian cases, there's the same number of sectors, and they match with each other, and they will be swapped. And once we match those sectors, we'll see that before and afterwards, the low energy spectrum look exactly the same. And that's my claim about these kind of dualities. Okay. And my next example I want to talk about is a slightly more complicated version than Kremers-Vanier. This is related to the so-called Kennedy-Tasaki duality. Do people call duality or just Kennedy-Tasaki transformation, maybe? And I think this is also not the first time Kennedy-Tasaki has been talked about in this summer school. And I want to talk about it again. And I want to talk about it to demonstrate that these kind of duality is actually we should think of it in a slightly more general way, that it's not usually because when we say duality, it seems like it's between two things. It's one model mapped to another model, and of course, in the case of Kremers-Vanier, it's just the same model, but one phase mapped to the other. So with this Kennedy-Tasaki example, I want to show that it's actually a permutation among many phases. So some people call it triality, or if there are three, or some other words. And then because there are more phases, there are also more critical points. And this kind of duality will also map between these critical points and relate the critical points to each other. Okay, so the critical points will also behave like this, that the critical points are pretty much the same, except that the sector labels are changed. So when we talk about, let's say, for example, 1 + 1 DCFT, and we want to form a partition function, when we need to decide which sector to add into the partition function, then things might change a little bit. Okay, so that's why I want to talk about the Kennedy-Tasaki. Okay. Oh, I want to say that I failed to provide any reading reference for my whole lecture, because we're supposed to finish a paper some time ago, but we're still working on it. So hopefully this whole thing, including all the top boundary change and sequential circuit, will come out very soon. But I've written the lecture notes, so I hopefully will at least post this lecture note very soon. But for this part, and in particular, the mapping between the critical point, there's a very nice discussion about that part in a paper by Meng Cheng and Shengjie Huang. So I'm writing the archive number here. Okay. So Kennedy-Tasaki is at least the way I first learned about it. It's about somehow trying to understand what we now call SPT phases in terms of symmetry breaking phases. So it's one-dimensional chain with Z2 cross Z2 symmetry, and famously there's a non-trivial SPT phase. And famously, if you put it on an open chain, there's fourfold degeneracy. And Kennedy-Tasaki came up with a mapping such that these fourfold degeneracy on an open chain can be mapped to the fourfold ground state degeneracy of complete Z2 cross Z2 symmetry breaking. Right? So if Z2 cross Z2 is completely broken, we should have fourfold ground state degeneracy as well. So it kind of maps the edge degeneracy to a bulk degeneracy. And because of that, the local operator parameters distinguishing these four degenerate states become the string operator parameter of the SPT phase distinguishing the edge modes. Okay, so that was originally the intention. But now I'm talking about in a more general way as a way to permute the whole phase diagram, not just from the SPT phase to the symmetry breaking phase, but there are actually 6 gap phases with Z2 cross Z2 symmetry. You can partially break the symmetry. You can completely break the symmetry. You can not break the symmetry and being in the trivial or non-trivial SPT phase. So there are altogether 6 phases. And I want to talk about this complete permutation of the phase diagram induced by some transformation, and then see how they also relate the critical point between different phases. Okay, so the way I'm going to do it, of course, is not directly work with 1 + 1D Z2 cross Z2 spin chain, but rather to directly put it into the sandwich construction and then see how the top boundary change will induce this transformation. It's actually easier to do than literally write down the Kennedy-Tasaki transformation. Okay. Okay, so I won't draw lattice Hamiltonian anymore because it's too much work, but rather I'll just talk about it in a more pictorial way. And the picture is that the bulk is no other than 2 copies of toric code. Okay, so just 1 copy of Z2, the other copy of Z2. So, or we call Z2 cross Z2 gauge theory, and it's the non-twisted version of Z2 cross Z2 gauge theory. So it's very simple. 2 + 1D. So the bulk is 2 + 1D Z2 cross Z2 gauge theory. And then the anyons is just 2 copies of whatever is contained in toric code. There's an E1, there's an E2, there's an M1, there's an M2, and they're composite. Okay, there are 16 anyons. Okay, and then the top boundary, we can have different choices. So you can use the rule of Lagrangian subgroup as discussed by Caroline the other day to figure out which subset of the 16 anyons can be condensed to obtain a gap boundary for this Z2 cross Z2 gauge theory. And it turns out there are 6 ways to do it. Okay, so there are, let me write down all the 6 ways. So write it as A1. A1 condenses all the charge. Right, so this is like taking the 2 copies of toric code and just condense charge in both of them. And A2 is a mix. A2 condenses E1 and M2. And A3 condenses M1 and E2. And then A4 condenses the composite. E1, E2, M1, M2, and psi 1, psi 2. And A5 condenses all the fluxes, M1, M2, and their composite. And then finally, A6 is the interesting one, where it condenses M1, E2, and E1 M2, and then also psi 1, psi 2. Okay, so you can check that within each A, the thing I've written down, they're bosons and they're mutual bosons. And moreover, once I condense everything within each A, then everything else gets confined. Okay. So after the condensation given by each of these A's, there's nothing left, and we get a gap boundary to vacuum. Okay, so there are 6 boundaries. Okay, so these are the 6 boundaries I can put on top here. And once I put the top boundary into one of these 6 gap states, then I automatically determine which one of the string operators in the bulk give us the symmetry operation and which one gives us the flux sectors. And you can check, because this is a very simple case. Everything is, all the anyons are Z2 anyons, and they're all abelian. So no matter which boundary we choose, we get sandwiches with Z2 cross Z2 symmetry. Okay, so so all 6 sandwiches are a one-dimensional spin chain with Z2 cross Z2 symmetry. So nothing tricky like this. So for the toric code, we changed the symmetry before and afterwards. But for this one, it's the same symmetry before and after. So you might say that this is a self-duality of some sort, that the system maps back to itself with the same symmetry after the transformation. Oh, sorry, this is again periodic boundary condition on the 2 sides. Yeah. Okay, I think the only thing I have time to talk about is if we correspondingly put the bottom boundary also in one of these 6 gap states, then what kind of gap faces we get. Okay, I won't try to exhaust all possibilities because there are 36 of them. But I'll focus on the situation where the top boundary is A1 versus A6. So I'll list all the gap faces in these 2 situations. And then tomorrow, we'll talk about, once we change between these 2 top boundaries, how the faces get permuted and also how the critical points map into each other. Okay, so the top boundary is either A1 or A6. Can everybody see? And then the bottom boundary can be 1, 2, 3, 4, 5, 6. Okay. And we'll be able to determine, given the top boundary and the corresponding gap bottom boundary, which gap face of the Z2 cross Z2 spin chain the sandwich realizes. And the way we do that is by identifying whether there are things we can tunnel between the top and bottom boundary without costing energy, and that will literally tell us that there's some charge condensation going on, there's some symmetry breaking. Okay, for example, if we have A1 and A1, if both boundaries are A1, then we can tunnel the full set of E particle between the 2 boundaries, right? And from what we learned about a single copy of toric code, if we have a single copy of toric code, and then both the top and bottom boundary are charge condensation, you can check that, or you can go back to the notes and see that this is actually a symmetry breaking phase. And the simple way to argue about that is that we can now tunnel the E particle between the 2 boundaries. So because the E particle is condensed on the top boundary, so the M string operator becomes the symmetry operator. So if you can tunnel an E between the top and bottom without creating excitation, that means the symmetry charge is condensed. So that means the symmetry is broken. right? So if top boundary and bottom boundary are A1 and A1, then the whole Z2 cross Z2 symmetry is broken. So this is completely symmetry breaking. Okay. So this is spontaneous symmetry breaking to nothing at all, to no remaining symmetry, just symmetry group being 1. Okay. And similarly, if we have A1 versus A2, these two, then we can tunnel E1. But for the second copy of toric code, there's nothing we can tunnel, right? There's E is condensed on the top and M is condensed on the boundary. So if you think of it as two Ising chain, then one of them has symmetry breaking, the other one doesn't have symmetry breaking. So this is spontaneous symmetry breaking to Z2. Okay. And similarly, if we have A3, this is breaking to Z2, and A4 is breaking to Z2, and we have 3 copies of spontaneous symmetry breaking to Z2 because there's 3 Z2 subgroups of Z2 cross Z2. There's counting of 3 here. And if we have A1 versus A5, we see that nothing can tunnel, and this is still 2 copies of toric code, but with charge and flux respectively condensed on top and bottom. So this is a trivial SPT phase. SPT0, this is the trivial phase. On the other hand, between A1 and A6, nothing can tunnel, but it's a different SPT phase. This is the non-trivial SPT phase. Okay. So we can do a similar exercise for the second row and determine the symmetry breaking pattern and potentially SPT order. So it's almost the same. For example, this is the one that's for symmetry breaking, and this is the one to Z2, Z2, Z2. Except that now we also see 2 symmetric faces, but I don't think there's a way to unambiguously say which one is the trivial one, which one is the non-trivial one, because the trivial and non-trivialness of SPT depends on the tensor product structure, in principle, of the Hilbert space. And once we lose that in the sandwich picture, actually it becomes ambiguous to identify which one is which. But I'll just write SPT here. Okay. Of course, the Kennedy-Tasaki is this one, right? Once we change the top boundary, we map from the non-trivial SPT to the fully symmetry breaking phase. And that is the one that I'll spend more time talking about that tomorrow. So, okay, that's all for today.
The first row, you started with.
Yeah, the first row is just we got lucky. So the question is why in the first row we can distinguish between SPT0 and SPT1. So the first row I got lucky because in the first row, the top boundary is a condensate that can be split into 2 copies of toric code. So if I think of it that way, then I know that for each copy of the toric code, I'm in a trivial symmetric phase. And once I put that together, I get a trivial Z2 cross Z2 symmetric phase. So kind of because I know with this boundary, how do I map back to the spin chain? Okay. But for the second boundary, the condensate cannot be split between copy 1 and copy 2. And that introduces the ambiguity. Yeah, thanks for the question. And there was another one here.
So the one I circle is the red circle?
Yeah.
What the other ones? Would there be a sigma?
They're induced at the same time. So if you apply Kennedy-Tasaki, not to the SPT, but to the other phases, then they should transform like that. Yes.
So here you can apply gap boundary on different side of the sandwich flow. You also do that in Oracle?
Oh, yeah. Sorry, I should have made that clear. So here, for example, the top boundary is gapped by this ZZZ term. And if for the bottom boundary, we only have the ZZZ term, and then we kind of have also the smooth boundary at the bottom. So it's smooth boundary at the top, smooth boundary at the bottom. So M condensed and M condensed. And then we can tunnel M in between. That means the symmetry is broken. Yeah. So I can also apply to rough boundary. Did I erase it? So here, this is the rough boundary. And if I import this term on the bottom, then this is the rough boundary without the ZZ term. If I only enforce the X term, then this is the rough boundary on the bottom. So I condense E on the top, condense E on the boundary, on the bottom, and then I can tunnel E in between. But now the M string operator becomes the symmetry, so this is again symmetry breaking. Yeah, so it's very similar story. Yes.
The M string operator have an expectation value.
So, sorry, can you say that again? If I have both E1 and E2 condensed on the top and bottom boundary, I can tunnel E1 and E2, and then. MX. Yeah. So that's spontaneous symmetry breaking. So in the ground state, you can both have no charge or charge. Yeah, so it's just the usual story of symmetry breaking, spontaneous symmetry breaking.
All right, let's thank you again.